Hello, math friends. Today we're going to be looking at Chapter 6, an introduction to continuous probability distributions. Well, in particular, just one of them, and I'll get into that. So Chapter 6 is really a continuation of what we saw in Chapter 5 and Chapter 4, so it's still the overwhelming arcing theme for this I call it like the middle third of the class, is investigating probability. So in particular, we started with the story of, ooh, what is probability? And as we were traveling down that journey, we saw two different distinct types that we're going to be investigating, discrete and continuous. And last time we saw discrete distributions in looking at the binomial. Today we're going to be looking at its continuous cousin, aka the normal distribution. Now, if you look at outcomes 4 and 5, you'll notice I have them crossed out because we will not be doing them, but there are some other continuous probability distributions. So if you'd like to investigate those are found in section 6.3, so you can check those out if you want to. The uniform is pretty easy to understand and what it's up to, and pretty straightforward. And there are quite a few things in the world that behave like a uniform distribution, so that's kind of fun. The exponential is also very useful, but a little bit more difficult to understand and not necessarily something all of you are going to ever see. In fact, I would say there is probably a very, very small set of you who it's probably less than like 0.001% of you are ever going to need the exponential probability distribution. It's a little bit like the hypergeometric, which I mentioned in Chapter 5. It's just not as common. That being said, if you're curious or interested, you can go check those two out. We're going to be focusing on outcomes 1, 2, and 3, which are all about using the normal and the specific standard normal distribution. So I'm going to introduce you to what those are and then how we're going to use them. So just as a reminder, continuous means that there's an infinite number of options. So unlike the discrete distribution where you can count how many options we have for outcomes, we're not going to be able to do that today. So the picture for this looks very different. It's because there's an infinite number of options. So let's get into that. I'll say more in a minute. So we're specifically going to be looking at the normal probability distribution. Now it has some distinct characteristics that make it look the same way every time, despite how wait, I was going to say despite something, but I've lost my train of thought there. So the big thing with the normal probability distribution is that it always looks the same no matter what kind of data you're looking at if it's normal. And that's kind of how it got its name. It's the one you normally see, which is kind of funny because it's really popular and really common. Anyway, so it has a distinct bell shape that makes it unimodal and symmetric. So as you're thinking about this, think like a bell with a peak in the center and both sides being the same. And there's a drawing of one on the next slide, so that should help you out. And since it has this unimodal and symmetric behavior and a bell shape, this means that when you look at the mean, median, and mode, or your three measures of center, they're all going to end up being the same because you only have one peak because it's unimodal. Let me take a look at the graph. This will help you out. So here is what a typical normal distribution's shape is going to look at. So I've labeled the mean, median, mode here at the center, so you can see that. And you'll notice that I've labeled each sides of the probability as 0.5 and 0.5. So if you remember the rule of total probability that we had from Chapter 4, that told us that the sum of all probabilities for any probability model where it encompasses all possible outcomes must be 1. And here we've got our random variable x down along the axis, and we're looking at a continuous range of values along the x-axis. So since it's an infinite number of values, notice that we have a nice smooth continuous curve. If you forgot what a continuous curve is from algebra, it's a curve where you can draw it without lifting your pencil. So you'll notice with this one, oh, I'm going to try to do outlining. This is going okay. Hopefully this is going nice and smooth on you're watching on YouTube. So again, this is a continuous curve. That's where the name continuous data comes from also, because there's an infinite number of options and there's no breaks or jumps or anything like that. It's just all possibilities. Now this looks very distinctly different from the binomial. So just a reminder, up in this little corner, I'm going to draw you what like a binomial looks like. We saw a couple binomials that looked like, ooh, my rectangle's bigger than the other rectangle. They would have some options like this. And some of them did look fairly normal where they were pretty symmetric. I've drawn one that's got a distinct right skew. And the reason they looked the way they did is because each bar represented one outcome. And because each outcome was countable, there was one of them, and it had distance 1, and then its height represented probability. That's all she wrote for that. And then when we were doing some of our calculations using Minitab and other tools, we would shade in area to get probability. And some of the similar ideas are going to happen here. The difference is I'm not going to have rectangles. I'm going to have this nice, smooth, continuous curve. All right. So the normal distribution is completely determined by its mean and standard deviation. So if you look over on my graphic here, I've got some different means you'll notice. So as I increase my mean, the location of my graph changes. So instead of being centered at 20, it might move over to 30 or 40. And then my spread changes as well. So if my spread is fairly small, it'll be a tight, tall curve like what I've got in A. If it's fairly wide like I have in C, you'll have a flat kind of less bell-shaped looking guy, more like a lazy hill that would be easy to jog up and down. Anyway, but you'll notice that the symmetry maintains the same, and this change in shape where we make it a little bit more elongated or maybe a little bit more tall maintains the area idea for probability, so that each area is a half on each side. So keep that in mind. And that's why when we describe the normal distribution, we only describe it usually in terms of its mean and standard deviation, because once we tell somebody it's normal, they know it has to have this distinct bell shape. And if you know the mean, you know where the center is. And if you know the standard deviation or the spread, you know how wide or flat it might possibly be. So it's completely determined by these characteristics. That's the way we'd say it mathematically. Here is the actual mathematical function for the normal probability density function. So when you see density, be thinking area, because that's how we did it and how we have been doing it, area of the bricks. But in this case, since it's a smooth curve, it has to have some sort of closed function form that you can use. Please note, this may look very intimidating. We will not be using it to do any calculations. We're going to use technology because it is much easier, and we're going to use some tables in case that's what you would like to enjoy. So you'll notice that with this video, there were two documents. There were the notes, and then there was the standard normal distribution table, or the Z table. And we're going to use that in a few minutes. So basically, the idea is that if you look at any continuous value from your random variable, whatever it might be, knowing the mean and standard deviation, you can create the normal curve. Good times. What you might find interesting is this has pi in it, and you're like, where on earth did that come from? Why is it an exponential? Why are there so many squares? If you would like to know, please take calculus. I actually teach this in my calculus class on how to do it. And when we go to do area, we're going to do something called integrating it. So if you've had calculus before, if I wanted to, you can integrate this function, but it's actually really hard to do. You need parametric methods to do it, so that's kind of fun. Usually when I write it, I like to write it like this, but it was difficult to get it typed in here. And so if you want to do area between A and B, that's how you do that. dx. Woohoo! Area. Those of you who have zero interest in calculus, don't worry, you don't need it to do this. We have other tools that will take care of that for you. Let's get into it. So the first tool we're going to use for this is the empirical rule. And I'm going to warn you, big like warning down at the bottom, this should be in red, but for some reason I can't get it to change colors. Only use this when you're told to. The big thing is this is a rule. Rules in mathematics are estimating tools. This is an approximation, and it's not exact, which means that it'll give you roughly an idea of what your values are going to be, or a rough estimate of what's going to happen, but it's usually a very rough estimate. So when you see this, be thinking, you know, this is an estimating tool. So if you need exact values, this is not what you should be using to do your calculations. So if you're looking to do some like budgeting or making sure that you're not losing any money, please do not use the empirical rule. However, if you're just trying to forecast what your sales next quarter might be, this is a great tool for that because it's good at estimating. Anyway, so the essence of the empirical rule is that if I look one standard deviation away from my mean, that's what this part is, and the plus and minus is just telling you I'm going to add, so go to the right by 1, and then the minus, you'll also go to the left by 1 standard deviation. So 1 standard deviation away in each direction, that gives me about 68% of all of the data values that are possible for that variable. And then if you go 2 away, that's 95, and if you go 3 away, it contains virtually all of that. If you want to know how much, I really should have written this in, it's 99.7%. So the other name for this rule is the 68, 95, 99.7 rule. Ooh, that 7 looks rough. It'll be okay because that's the exact values that it gives you. So 99.7%. So be thinking, if I go 3 away, I've got everything but the last 0.3% of all data. Not 3%, 0.3. It's not a lot there. Anyway, so that's like 3 thousandths. Be careful with that. So if you remember back to when we were talking about z-scores, I made a remark that when you are about 1 standard deviation away, you're not unusual. Yeah, you're near the halfway markish. That's not strange at all. When you get to be about 2 away, you're quite unusual because you're in the upper 5% of all possible data or the lower 5% of all possible data. And you'll see how this looks when I show you the graphic next if that's a little confusing to you. And if you get 3 away, you're incredibly unusual. Yay! So, because you're in the, tail 0.3%, either in the upper or lower end. Let's look at the graphic. This will help you. Here you go. So it's basically saying that if I calculate a value or randomly pick a value from a distribution, it's in here. Oh, it's not unusual. Its z-score is going to be around 1 to -1. So this cutoff value right here is mu plus sigma. And this is mu plus 2 sigmas away. I actually don't like this nomicker. It makes you think you're only going 1. This value right here is going to be mu minus sigma, and then mu minus 2 sigma. So if I randomly selected a value and it ended up like here, boom. If this is 95%, then this out here, that's in the lower 2.5% of all possible data. Very unusual and very low and unusual. And you can use z-scores to tell that as well. And we'll get a little more into that in a little bit. Here's a little bit more of a detailed breakdown that's written a lot better than the one I just did. And this is the, I know I said approximate areas, but these are more exact. So you know how I told you 99.7? Well, this is much more exact. 95, well, it's a little bit bigger than 95. And 68, it's a little bit bigger than 68%. So be careful when you're using the empirical rule. It's an estimator. It's not exact. One thing that's nice about this is you can also use symmetry to get exact values off of this. So keep that in mind as well. Alrighty, so suppose you wanted to use the empirical rule to do some quick calculating. So if you're looking at travel distances for an Uber service in a major city it has a relative bell-shaped distribution with a mean of 15.1 miles and a standard deviation of 3.1 miles per trip. So we want to use the empirical rule to estimate what the possible distances might be using probability. So assuming that this is a bell-shaped distribution, which we should know because they say that you're going to use the empirical rule, be careful. You really shouldn't use the empirical rule if you don't know it looks relatively normal or has some of the normal distribution's characteristics. Otherwise, your estimates are going to be really far off. Anyway, so we want 68% of all trips. Well, that means I want to take my mean and add and subtract 1 standard deviation away. So I've mentioned this before, but the plus or minus symbol means that when you're doing this calculation, you're just going to go through and do it once with plus, and that'll give you the upper end up here. And then you're going to go through and do it with minus and this lower end up here. So really plus or minus means that you're going to be doing 2 calculations, and it's really just born out of laziness. Unfortunately, it's one of those things where math people, because this comes up so often, decided they were going to write a shorthand for it, hence this plus minus symbol. So this tells us that about 68% of all trips are between 12 miles and 18.2 miles. That tells you that if you have a driver that is consistently reporting that their trips are around 20 miles, that's not too unusual because it's, fairly close to the 68%. But if they were saying 30 miles, you should be like, whoa, whoa. That's not happening, yo. Anyway, we can do the same thing. I do have a little bit of a typo here. That should be a 2, not a 1. I just noticed that. Oops. So 95% of the trips should be between, well, you want to do 2 in each direction to get 95. So notice the 2 here. I'm sorry that I messed it up over on the earlier one. There should really be an equal sign here too. I wonder if it just didn't save the last time I edited this. Tisk, tisk. So to calculate this, you'll do 15.1 plus 2 times 3.1, or it's the equivalent to adding 3.1 twice. Remember your order of operations. You should do your multiplication first and calculate this and get 6.2 before. So I'm calculating this portion. And before adding it to the 15.1, and that will give you 21.3 miles. And then if you take 15.1 and subtract 6.2, you get 8.9 miles. And I wrote on that kind of terribly. Will it let me erase? Last time I tried to erase, it did something crazy. There we go. Nosh. Anyway, so this tells us that 95% of all of our journeys on this for Uber in this city in particular will be between 21.3 and 8.9 miles. So again, if you have a driver who's consistently saying, oh, my trips are always 30 miles about each, there's definitely very little chance that that's happening, especially if it's multiple trips. This is saying per trip. So that would be very suspicious if you were, keeping track of them, except for, Uber is sort of self-automated. So I don't know how well that was going to work for them. It was kind of interesting. Anyway, so what we can do is we can actually use the normal distribution and some tools to do other probabilities as well. So all I've done so far is I've used the rule to do some estimating. It would be nice to actually use it to do some calculating for specific values rather than just estimating specifically only 68% and only 95%. So because we have continuous random variable and we have probability, we're going to use area to create probability. So I've got this diagram down below. The yellow portion is the area. You use a range of values, an area under the curve between two values or below or above two values to get yourself some area and probability. So one thing to keep in mind is that since area creates our probability just like it did with the binomial I drew earlier. Remember, the bricks were colored. They were actually making area to get probability. You can't get probability from a single value. So I make note of that right here at the beginning. So just looking at the probability that one value happens, like x2, well, that has no area. It's a line. Lines have no thickness, and therefore your probability for that single value would be 0. That's why we're going to be between two values, and we're also going to do stuff with lefts. So x minus some x2 value or rights. So notice I've started dropping the equal to's because I actually don't need them. So if whether or not it's equal to in value does not matter since a single value has no probability. Let's do some examples with this if this makes you uncomfortable. My examples should help, and the mini tab for this week should help a lot too because, well, it's a lot of calculating areas using mini tab. So we're going to start working with what's known as the standard normal distribution. It's called the standard because it's the one that comes from using the standard scores or z-scores. The other reason is it's also the one we end up using all the time, hence it's the standard for normality. Woohoo! So it's going to be using z-scores. The biggest characteristics that this guy has is that he always has the same mean. Notice his mean is 0 and his standard deviation is 1. This is always true for all standard normal distributions. So the one I just did with Uber had a specific mean and specific standard deviation that were based on that city. In a different city, they would probably be different values. However, when it comes to the standard normal distribution, it's always mean 0, always standard deviation 1. And you'll notice that since it is z-scores, you'll notice on the axis I'm going to be using z instead of x because it's actually a different variable. It's one we know and are familiar with. And just in case you forgot what the z-score was, here it is. So remember, z-score is telling us how many standard deviations a particularly x value is away from the mean. So you do x minus the mean and divide by standard deviation. So x is always your value of interest. So essentially what this is going to do is it's going to take your value of x on some x distribution and transfer it over to this guy, the standard normal distribution. Yay! I'm going to show you how we do that. And we'll do our calculation on the standard normal distribution for reasons you'll see. Anyway, so any normal distribution will always have its own specific combination of mean and standard deviation. We've already seen from our first little look at the ABC thing earlier that those completely determine what the distribution looks like, but we can convert them to the standard normal distribution using z-scores. So let's look at an example using this, and this will hopefully help you out with understanding what's going on here. So we suppose that we're looking at a SUV, and their gas mileage is normally distributed with a mean of 22 miles per gallon and 4 miles per gallon. This should have the units in it as well, because one of the reasons we like the standard deviation is because it has the same units as the mean. Good times. So suppose we were interested in figuring out what's the probability one SUV gets less than 26 miles per gallon. So what we could do is we want to say I want all this stuff in here. So I'm hoping you notice you're like, oh, I can estimate this using the rule. I know that half the distribution, so this is stuff to the left of 22, that's 0.5 because it's just half. And then the stuff here, well, that's one standard deviation away from the mean because 22 plus 4 is 26. So this is the same as z equals 1, and I'll get into that in a second if you're not sure that I'm right about that. It's one standard deviation away, which if you go one standard deviation away in each direction, that would be between 18 and 26, and that would be 68% of all data. But I only want this half of it, so that's 6/8 over 2. Which would be 34. So I can just look at this and say, oh, this is going to be about 0.5. Oh, no, wait, I got to add 5 to this. 0.5 plus 3, 4. That's a 4. Doesn't look like it. So this should be about 0.84. Let's actually calculate it using the tables, because that'll be more exact than estimating using the rule. So this is approximate. So just to recap what I did here is I said, oh, when I look at half the distribution, the stuff over here, that's half, so 0.5, and the stuff between here, that's half of the 68% of the empirical rule. So I'll just take that and divide it in half, and then I combine those two to get 84. But again, I can use the rule, but it isn't exact. It's not perfect. Let's try something that's going to be more accurate than just saying, 84. It's probably right. It'll be close. So if you take the probability you're interested in, which is this area, based on this z-score in particular, x, because that's the variable I used for miles per gallon, is x, I can transfer it down to being a z-score by doing z equals x minus mu over sigma. So I took 26, subtracted 22, and divided by 4, and got 1. That's where this came from. And then z is equivalent to doing that. So this is all going to be the same area. So all I did was I took it on this distribution and dropped it down onto the standard normal. And notice they're the same. So by calculating it on the standard normal, I'm going to get the same probability. Let's do that. So I'm going to pull out the probability table, and I have a typo here. So there's supposed to be something that came up in red right here, but it didn't. So the area right here, that's the probability that z is between 2 and 0. Sorry, not 2, 1 and 0, which is 0.3413. And then I'm like, oh, but I want less than or equal to 1, not just 1. So I need to take this, that 0.34, and add a half to it. That's a 1. That doesn't look like anything. Let's fix it. 3, 1, 3. Okay, so that's 0.8413. Nifty? And a lot more accurate. If you do not like using the table, we're going to show you how to do this using Minitab as well. And I like the Minitab way a little bit better. It's a lot less work. And all you have to give Minitab is this information and the mean and standard deviation. You don't have to do any of this converting or coming up with X or looking it up on the table. So just to make sure we're understanding the table, I'm going to do a second one where I need to look up a couple different values, and I'm going to use some stuff that's not in the first column. So if you've been following along, I've only used first column stuff so far. I need to show you how to get other decimal places as well. Speaking of, let's do that now. So suppose we're going to look at a particular value for the SUV, and I'm like, hey, instead of doing something that's exactly on one of the standard deviations, let's do between 23 and 27. So I'm picking this because it doesn't fall exactly on 1 or 2 standard deviations away, and there's 2 of them. So I want in between. So I want this value. Whee! So I'm going to show you how to do a couple things here. One, I'm going to do some stuff where I don't have perfect values, and in particular, I'm also going to have stuff where I'm doing an in between. So here's my area of interest. I'm going to look up my two z-scores and convert it over. So not look up, I'm going to calculate my two z-scores. So I'm doing z for once for 23 and then once for 27 to come up with the two z's that are equivalent. So I'm going to be making this into the probability that, okay, so you look at the one for 23, that's this, 0.25 less than or equal to z, not x, because I'm now on the z distribution, and then 1.25. And all I did to get these was I subtracted the mean and divided by standard deviation. And as a reminder, notice that this fraction, because this is a common place where people make mistakes, is not the same thing as 23 minus 22 over 4, because that is only dividing the second value by 4. If you're having difficulty with this on your calculator, maybe do it in 2 steps, 23 minus 22, then divide by 4. I've noticed that in particular on some of the scientific calculators, if you put this in all in one step, it'll definitely give you this version, which is the incorrect one, not the correct one. So double check, calculate this yourself, make sure you get the same value I did. Anyway, so I've tried to label these on here, which I was not as successful as I thought I was on the picture. So I'm interested in this little area that I've placed in pink this time for fun and pinkiness. So those of you who are colorblind, enjoy the fact that that's what pink looks like. I don't know. So I'm looking at this value and it doesn't fall perfectly on some z-score values, some whole numbers, or even halves. So it's going to get a little wild. Let's look some stuff up. That's the wrong one. Crap. Okay. So in our adventures with typo land, we have another typo. This is like all wrong. All right, here we go. We'll fix this. It'll be okay. So I need 0.25. So here's 0, 1, 2, 3, 4, 5. I've made the common mistake of grabbing the value that goes in position 5, which is actually incorrect. I need this one. So that's the one that's 0.2, 1, 2, 3, 4, 5. There we go. And the same thing down here, I need 1.25. So I go down to 1.2 and then I need to get to 0.05. So that's 0, 1, 2, 3, 4, 5. So it's this one instead. Now here's where you got to be careful. Since I'm looking at the area between these two, I just need to subtract them from each other to get this. So to get between 0.25 and 1.25, I'll make sure when I do my copy of the notes that this is correct, so you don't have to have the same troubles. So this is 3,944 minus 0.0987. And hopefully this makes sense area-wise, since these are doing area up to 0.025 and area up to 1.25. All it's really doing here is saying, oh, what's the area between them? Well, it's just the difference of the two, which makes a lot of sense when you think about it. I'm pulling out my handy-dandy handheld calculator to calculate this for you. And you should get 0.2957. I apologize for the typo. I will make sure I correct that for the copy you guys get. Unfortunately, I can't fix it mid-video. Thanks a lot, Snagit. What's the name of the program I use? So we have to correct this on here as well. Whoops. 0.9. Or sorry, 0.29. Oh, that looks like not words. Hold on. 0.2957. 0.2957. Oh my gosh. I'm so glad you guys are watching this and that I'm not going to be able to edit it out because I know how this recording is about little small snippets. Anyway, so basically the idea is that the table gives you area between here up to 0.25 and here up to 0.125, and then just by subtracting those two you get the area between them. So that's what I was up to with doing the subtraction. So whenever you're going to end up doing between two values in the table, you have to use a subtraction to get the value between them, just like you would do to find the value between them if they were just numbers, not area. You just subtract them from each other. That's how you find distance. But in this case it's area because it's on the distribution and it's the probabilities that you're subtracting. Good times. Mathing. The other thing I would warn you about is that when you do this with Minitab, you won't have to do any subtracting because it'll just calculate it for you in one step. You just have to set it up right. So that's kind of fun. All right. Let's look at a left. So this is a little bit different because I'm looking at the area to the left of just one single value on the tables. So I'm going to look at tips left by a customer at a local restaurant with a mean of $12 and a standard deviation of $3. We're going to find the probability that you end up getting a tip of less than $8. Yep. Anyway, so again, my probability or area of interest is right here. I apologize for this. That should have been a -4. No, -5. Oh, that looks horrible. Anyway, let's just ignore that and pretend that life is good and that there were no errors on this. Just kidding. Anyway, if you've been paying attention to the tick marks on here, you notice I always place the mean at the dead center with a line, and then I count out my standard deviations to mark my values. Because remember, standard deviation is how we measure distance on a data set. So, and I'm just going down by standard deviations here. So I took 12 and I subtracted 3 to get 9, subtract 3 to get 6, subtract 3 to get 3. This should be 0. Subtract 3 to get -3. Fun. So then what we're going to do is we're going to take this value of interest, convert it onto z, and calculate it using the table. So we go down to the standard normal distribution by subtracting the mean divided by standard deviation. So I'm right here, and you come up with 1.33. So on the standard normal distribution, it would be 1.33, and I want this little purple area as my probability of interest. Yes, that's purple. This one. No. Okay, so I'm going to look this up on the table. Yep. So on the table, I'm going to need to look up 1.33, and I'm going to need to do it on the negative side, which if you flip that over, that would be 1.33 on the positive side. So we're using the symmetry here of where would 1.33 be? It'd be like here-ish. So I'm just going to look up this area instead, because that will give me the difference. Now here's where you have to be careful. Now remember, the table does between 0 and here. So what's unfun about that is that in order to get a tail like this, I'm going to have to subtract this from a half, because this is what the table is giving me. Table value. And I need the stuff on the other end, the tail. So I'm going to have to do a half minus that. And that's what I was marking over here is, oh look, this is the value you get from the table. So you look up 1.33 and you get the 0.0482, and you subtract it from a half, and that'll give you the leftovers and get slightly above 9%, or 0.0918. So the chance of you getting an $8 tip or less is 0.0918. So that's how you do a small tail on the left-hand side. And be careful, I know that these values on this standard normal distribution are positive, but you're using symmetry to get the negative side. So I drew the positive side over here and then just think, oh, well, it's the same area, because if I flip it over to the negative side, it's symmetric and so the same. All right, let's look at an upper tail now. An entrance exam for graduate students in a major university produces scores that are normally distributed with about a mean of 80 and a standard deviation of 50. This is the old GMAT, in case you were wondering. So we want to only enter students who score in the top 10%. So what should your cutoff be for admittance? So I want this to be 10%. So notice this question is very different from everything we've done before. I know the area and I want to know the value. So I need to go backwards, because in all of our previous ones, I've known the value and been trying to find the area. So if you look back at our previous examples, there was always the same step. We start out with an inequality, we convert it into a z, and then we use the table to find the probability. So I'm going to be doing this backwards. I'm going to find the table value using probability is what I know, back that up to, back that up to using the standard normal value to convert, and then turn that into a x. So I'm going to have the table, get a z, then use the z to calculate an x. Here we go. So we're going to start off by using the table to do this. So what's weird about the table here is my little bar thing is really far over. It should be right here. It's weird how sometimes when I open this, things don't end up lined up. Anyway, so the table value you get and that you're going to look up is 0.04. Because remember, the table does area close to 0, so it does this stuff. It won't do stuff in tails. So I'm looking up the value I can on the table. So what you want to do is you want to go and see if you can find the value closest to 0.04. So what I usually do is I start with the 0 column and I look down it until I get something that's close to it. So I look for the values that are below and above what I want. So we want to look at the rows 1.2 and 1.3 because you want 0.04, and these two rows have below 0.04 and above it. So looking down these rows, you just want to keep looking until you get close to it. So this one's getting bigger, that's not good. So the bottom row of 1.3 is getting too big, that's going to be not good. But 1.2 is doing the same thing, but that's good because it's going to get closer to 0.04. And then you notice right here, 1.28 is below 0.04, 1.29 is above it, and 1.28 is below but closer than 1.29. And it's not just that it's below, it's closer. So I'm going to use this value, 1.28, because it's the one that's 0.039999. So the z value I'm going to be using is 1.28 for that reason. So I'm going to be using 1.28 as my z. So far what I've established is when I look at z's greater than 1.28, that gives me close to the upper 10%. Now when we do this with Minitab, you'll be able to get the upper 10% accurately. You won't be looking at the table and guessing and picking the one, not guessing, looking at between two choices and saying, oh, well, I'll pick this one because it's closer. You'll get the exact value, which I believe for this one is actually 1.276 something. Anyway. So I'm going to take that knowledge and convert it. So I know my z, so I know z, put that in there. I know my mean, it's 800, put that in there. I know my standard deviation, it's 50, I'm going to put that in there. And then all you need to do is solve for x. This is the first place where you use algebra in this class. So just as a reminder, you are not doing the order of operations here because you are not calculating. You are going to be doing things for solving, which means whatever you're doing needs to be the opposite of what's happening. So since x is being subtracted from, is having 800 subtracted from it, I almost said that backwards, and then being divided by 50, what you're going to do is get rid of the last thing first. So since the last thing that's happening to x is divided by 50, I'm going to multiply both sides by 50 and then add 800, which is where this comes from. Now, if you're having difficulty with that, you can also remember that z values are giving you the number of standard deviations away from the mean a value is. So really, this is 1.828 standard deviations, which are size 50, away from the mean, which is 800. So look at this, 800 plus that. Anyway, so we need our students to be in the upper 10%, and to do that, they need to score above an 864 to be admitted to that university. Alrighty, let's do a lower for fun. So here I'm going to do a lower percentage, and this is going to look very similar. A maker of cell phone batteries determined that the time it takes between charges is normally distributed with a standard deviation of 1.5 hours. If a customer wants more than 5% of the batteries to require charging in 13 hours or less, what mean should this time be in order to be between charges? So here I don't know the mean, which is a little bit interesting, but I'm going to be able to calculate it using the standard normal curve. And you can only do this because it must be normal. So without this bit where it says is normally distributed, you would not be able to do this problem at all. You would have no idea where the mean would be. So this is kind of important. Alrighty. So the first thing we're going to do is we're going to use the z table to look up 0.05, since that's the lower tail probability I'm given for my x value of 13. And if you do that, you get that z is negative 1.645. I actually did this using technology, that's why it's 3 decimal places. And then you'll set up your equation. So negative, I'm using the z score value. So z score is x, which I know to be 13, minus the mean, which I don't know, divided by 1.5. So then what you'll do is you'll multiply both sides by 1.5, and then subtract 13, and you'll get something even more negative, and then you'll divide by the negative, and you'll get the value of the mean. Woohoo! So here's the steps behind doing that. Anyway, oh yeah, and here I am tricky. I was just like, oh, let's make it all positive. That was shady of me. This tells you that your mean battery life is 15.47 hours. So this is fairly typical for how they estimate how long something might last. They get a good estimate of the variation and what a couple of the values are, and then they look at the lower scoring values and use that to estimate the average. This is the way you can do it using a sample. Later on, we're going to see better ways to estimate the average other than this, and they're much better ways, and that's coming in just 2 chapters. So if you're wondering where else this gets used, it's a coming.